Hello, and in this fourth talk I want to highlight an important issue which causes a lot of people some problems when they start thinking about analysing AC circuits using phasors. And I'll start by asking a question. This question. What would be the amplitude of the voltage across the resistor, in this case at the break frequency? Well, if you remember from a couple of videos ago, if you're at the break frequency, then the amplitude of the voltage across the capacitor would be, in this case, V0, the amplitude of the voltage across the source, divided by the square root of 2. And obviously the amplitude of the voltage across the source itself is just V0. So what would be the amplitude of the voltage across the resistor? Quite a few people might answer D, thinking that if this is the amplitude of the voltage across the voltage source, and this is the amplitude of the voltage across the capacitor, then the amplitude of the voltage across the resistor must be, by Kirchhoff's voltage law, V0 minus V0 over root 2, or V0, or 1 minus 1 over root 2. And they'd be wrong. We can try it in the simulator. Here I've built the circuit, and I've set the frequency so that it's at the break frequency for this value of resistor and capacitor. And as you can see, as expected, the voltage across the capacitor has a magnitude that is the voltage across the voltage source, 1 volt in this case, divided by root 2. But what is the voltage across the resistor? The answer is it's the same as the voltage across the capacitor. It's the voltage source divided by root 2 again. So we have an amplitude of the voltage across the resistor, which is the voltage source divided by root 2, and an amplitude of the voltage across the capacitor, which is also the voltage source divided by root 2, and adding those up gives you the amplitude of the voltage source. What's going on? Well, you can probably see the answer by looking at this time domain plot of the waveforms involved. The blue is the voltage from the voltage source, the purple, the voltage across the resistor, and the green, the voltage across the capacitor. And you can see that the voltage across the resistor does indeed have a magnitude of 1 over root 2, and so does the voltage across the capacitor. But they don't have the magnitude of 1 over root 2 at the same time. If you look very carefully at this plot, you might be able to note that if you add the purple value, that's the voltage across the resistor, this one, to the green value, that's the voltage across the capacitor, this one, then at every single point, this voltage plus this voltage is equal to the blue voltage here, the voltage from the source. So Kirchhoff's voltage law does apply at every single point in time. But that doesn't mean that the amplitude of the voltage across the resistor plus the amplitude of the voltage across the capacitor is equal to the amplitude of the voltage across the voltage source. It isn't, because those amplitudes don't happen at the same time. What is true is that the phasor representing this oscillation, the voltage across the capacitor, plus the phasor representing this oscillation, the voltage across the resistor, is equal to the phasor representing this oscillation, the voltage across the voltage source. And you can see that in this diagram here. This is the phasor representing the voltage across the resistor. This is the phasor representing the voltage across the capacitor. If you add that complex number to this complex number, their imaginary parts would cancel out, but their real parts would combine and they would give you this resultant phasor. So Kirchhoff's voltage law works perfectly well if you use phasor representations of the sinusoidally varying voltages. What you can't do is use it just with the amplitudes of the oscillations. In this slide, I just want to emphasize that point. The magnitude of the voltage across the capacitor plus the magnitude of the voltage across the resistor is not equal to the magnitude of the voltage across the capacitor plus the voltage across the resistor. But what is true is that the phasor representation of the voltage across the capacitor, maybe I'll write that as VC phasor, plus the phasor representation of the voltage across the resistor, VR phasor, these are complex numbers, remember, is equal to the phasor representation of the voltage across the source. That is fine. The phasors contain information not only about amplitude, but about phase as well. And the phase is important. This, of course, is equally true for currents. If we had some component here and another component here in our circuit and another component there, and we were trying to solve this circuit using nodal analysis, and we had a current through the capacitor, a current through the resistor, and a current through the inductor, what we could say is that the phasor representation of this current plus the phasor representation of the current through the resistor is equal to the phasor representation of the current through the inductor. But what we cannot say is that the magnitude of the current through the capacitor plus the magnitude of the current through the resistor is equal to the magnitude of the current through the inductor. It isn't. We're losing the phase information. That's all for this time. Next time, I want to say a bit more about the equivalence of Ohm's law for capacitors and inductors.